So today we'll be looking at the topic of electric fields, and in particular we'll be looking at Coulomb's law. So basically Coulomb's law in equation form is this over here. The force equals 1 on 4 pi epsilon naught Q1 Q2 over R squared. That's what it is in equation form. In word form, the reason this came about is Coulomb found that if you had two stationary charges, they experienced a force along a line joining the two charges. Okay, and what Coulomb also found is that the forces were attractive if the charges were opposite, and repulsive if the charges were alike. Now this is what we expect, and I'll draw a little diagram now to show you exactly what this means. So basically what I've said is if we have two stationary charges, like you can see in my little box here, we've got two stationary charges next to each other, one here and one here. Now, they experience a force along the lines, along the line joining them. Okay, so if we were to draw a line joining them, they would experience a force along that line. Now, the force is attractive if the charges are opposite, and they're repulsive if the charges are alike. So you can see here we have two negatives. So this is going to be, because they're alike, a repulsive force. Okay, it would be the same if they were both positive charges. That would also be repulsive because they are alike. Now, if you come over to our next box, again, we're going to experience a force between the particles on the line joining them. Because they're opposite, they're going to be attractive. So what we'll see is if we can imagine this on the left-hand side as two electrons, they're going to be repulsive, so they'll move away from each other. And on the right-hand side, our positive and negative, they're going to be attractive, so they're going to move towards each other. So that's basically Coulomb's law. Now, it's represented by this equation here. F equals 4 pi epsilon naught Q1 Q2 over R squared, and we're going to go into that now. Okay, so as I've said, this part here, 1 on 4 pi epsilon naught, this is a constant, all right? And the value of it is right here, and that's going to be given on formula sheet. You don't need to remember that, okay? We have Q1 and Q2. Now, Q1 and Q2, these are the values of the charges, okay? And they're measured in coulombs, and we'll talk about that in a moment. And R is the distance between the two charges, okay? So if you're given a question, you'll be given all of these numbers. Now, we see this little epsilon naught. Just want to highlight the fact that this is called the permittivity, and it's associated with the vacuum, because whenever we deal with a problem at our level, we'll be looking at inside a vacuum. Now, the next top point I've said is how is it consistent with Newton's third? So Newton's third says that every reaction has an equal and opposite reaction. So what that means is when we calculate this force, if we think back to our two negative particles, if there's a force on one of them and we calculate it, it's going to be the same as the force on the other because they're equal but opposite. All right. Now the last point I've got on there is, does this look familiar? Now the reason I put that up there is because it should look familiar to you, because we've just been dealing with gravitation and satellites, and we had this equation, F equals G, which was a constant, M1 M2 over R squared. Okay, so that was the gravitational force attracting between two particles, and this is the electrostatic or the electric force between two particles, Coulomb's law. So these look quite similar, and when they're used in the same way, and we'll have a look at an example of that in a minute. All right, so just a couple of facts here. The unit of charge is a Coulomb, as I've stated already, and 1 Coulomb is huge. All right, so when we're dealing with newtons in forces, we say 1 Newton, that's not a lot. All right, but 1 Coulomb, that's a huge amount of charge. When you think about rubbing a balloon, as I've stated down here, that's approximately 10 to the minus 8 coulombs, so a really tiny amount, 0.0070 zeros and then 1, so a tiny amount. So if you did have a 1 Coulomb charge, all right, and you separate it by a kilometer, so that's a pretty large distance, the force produced by it would be 9,000 newtons. which is enough to lift a small car. So if you get an answer and it's in the term of coulombs, all right, you probably have done something wrong with your working out, and you probably need to just check your if you've put a minus instead of a plus, or vice versa with your equation. So an example now. 1. Calculate the force of attraction between two charges. Q1 is negative 1.0 by 10 to the negative 6, and Q2 is plus 2 by 10 to the negative 6. They're 1 meters apart in the vacuum. So we're going to use Coulomb's law that we just had a look at. Force equals 1 on 4 pi epsilon naught Q1 Q2 on R squared. And we're basically just going to substitute in our numbers to this equation. Now, the first thing I want to note is I don't actually have to put the negatives in or the positive. That just indicates if one's negative and one's positive, we know the direction. They're going to be attractive forces because they're opposite. So what I can do now is just substitute those numbers in. So I've put those in. I've just changed this part here into the constant 9 by 10 to the 9. My Q1 is 1 by 10 to the negative 6. Q2 is 2 by 10 to the negative 6. And my R has to be in meters. So it's 1 meter squared. Now, the most common mistakes people make here is often this isn't given in meters. And you need to always change it back to meters. And often you need to make sure you square it as well. That's a really common mistake. So all we do now is put that into our calculator. Okay, and if you put that in your calculator, we will get 0.018 coulombs. And remember that a force, and that's exactly what we've calculated, a force has a direction, it's a vector, and that direction is attractive in this case. Although the way I've written attractive isn't very attractive, that is the direction. And actually I've made a very beginner level error because I've written the force in coulombs when we know that the force is always written in terms of newtons. Okay, so this should be 0.018 newtons. So if you got that, really well done. All right, so part 2, we've been asked to calculate how the force would change if the distance between the charges doubles. All right, so I've just brought over the force that we know, and I also want to put in, so the distance between the charges double, so R becomes 2R. And we know that the force is proportional to, we want to see how it relates to R. R's on the bottom and it's squared. Okay, so we can write, this means force is proportional to 1 on R squared. So if R changes, it's going to change by the inverse square. So what I want to do is I want to make R double, go to 2R. So that means our F is now proportional to 1 over 2R. So all I've done is change my R to 2R. And I want to make sure I square that 2 as well. Okay. Eventually I get 1 on 4R squared. All right. So what I'm doing, if I double my force, what this means is my force becomes 1/4 of my original force, which is 0.018. Okay. So then you just chuck that in your calculator. And therefore, the new force equals 4.5 times 10 to the negative 3 newtons. Okay, so that's the first one, part I. So part 2, our distance between our charges is reduced to 25 centimeters. We started at 1 meter, now at 25, so our R has become 1 over 4R. All right, and we know our force is proportional to 1 over R squared. All right, but now our R is 1/4. We need to make sure we square that whole thing. All right, so therefore, if we square that, we are left with force is proportional to 1 over 1 on 16 R squared. And remember, if we've got a fraction in our denominator, we can bring that up to the top. So therefore, our force is proportional to 16 on R squared. So our new force, if we make it a quarter of the distance apart, equals 16 times by 0.018, and that equals 0.288 newtons. Okay, so that's the second part. Let's go to the third now. So part 3 says that what would happen if Q2 was the same as Q1. So Q2 becomes half Q2. Okay, because at the moment it's 2 and it goes to 1, and it also changes sign. So our force is proportional to, directly proportional to Q2. Okay, so if that becomes half, that means our force is becoming half as well. So therefore, our force equals half times by 0.018, which equals 0.009 newtons. Now, we've got a different sign now. So now they'll both be negative. So therefore, this will be a repulsive force, and we need to make sure we write that. Okay, thank you.